9.4 continued here. We use the Greek capital letter sigma to indicate a sum. Okay, that was bad. Let's try that again. There we go, a little bit better. We also use limits, or the least and greatest values of n in the series, to indicate how many terms we are adding. So limits tell us the lower limit and the upper limit, the smallest number and the biggest number. Okay, for example, we can write this series right here as the summation n equals 3 is our smallest number that we plugged in, to our biggest number, 108. And we use our explicit formula here, n squared. We took a number and squared it, next number and squared it. Okay. 108 is called our upper limit, n equals 3 is the lower limit, and n squared again is that explicit formula for the corresponding sequence. For an infinite series, we use infinity as the upper limit, and that becomes more and more common when we get into further math. So those of you taking calculus, for example, will use that quite a bit. To find the number of terms in a series written in summation form, with sigma there, we subtract the lower limit from the upper limit and add 1. Okay, so here, we'd have taken 108 minus 3, and then added 1 because we did both endpoints there. We did 3 and 108, so we have to add 1 and gotten 106. Okay, that would have been the number of terms in our series. Example 3, we are going to write this in summation notation. So, first thing we need to do is our lower limit here is just going to be 1. Okay, that's where we're going to start with the first term. So n equals 1. We don't know what our biggest term yet. Okay, we don't know our our number of terms. We don't know where we end at. So we have to figure that out. We also need to figure out our explicit formula to put in our summation here. So explicit formula, a sub n equals a sub 1 plus n minus 1 times our common difference. 7 to 11, we add 4. Here we add 4, add 4. So we're going to add 4 all the way through. That's going to be our common difference. Okay. First term is 7. N minus 1 times our common difference of 4. We can go ahead and simplify here. All I'm doing is distributing. And now I'm going to combine my like terms. So, this right here is my explicit formula for my sequence in simplified form, and that's what I plug into my summation. Now, I still need to know what my n value is, my final n value. So I take my last term and I substitute it in. The value of my term is 207, and I can solve for n here to figure out my n value. Subtract 3, 204 equals 4n, which means n is going to be 51 when I divide by 4. So, 51. I have the summation from n equals 1 to 51 of 4n plus 3. And that is my summation notation. Now, summation notation for the following series. Okay, again, we're going to start off with sigma, and we're starting with our first term. We don't know our nth term yet. We also don't have our explicit formula. So those we're going to have to find. Explicit formula a sub n equals our first term plus n minus 1 times our common difference. Negative 5 to 7, to 2 we added 7. To 9 we add 7. To 16 we add 7. Here we're going to add 7 as well. So that's going to be our common difference. Our first term is negative 5. So we can plug those in. A sub n equals negative 5 plus n minus 1 times 7. I'm going to go ahead and simplify this. And again, all I did is distribute here. Combine my like terms, and I get a of n equals negative 12 plus 7n. And again, that's because I combine these like terms. So this is the value of my function I'm going to use in my summation. Negative 12 plus 7n. You also could have done 7n minus 12. Either way, mean the exact same thing. Now, I need to figure out what this n value is. So I use my last term in for a of n. And that's going to help me figure out my n. So 268 equals negative 12 plus 7n. Add 12 to get my 7n by itself. 280 equals 7n, divide by 7, and n is going to be 40, which means that 268 is my 40th term, and we're going to go from our first term to our 40th term in this sum. Same idea here for b. Again, go ahead and pause and try if you'd like. Summation. Starting with my first term. The only time it would not be the first term, guys, is if we have like dots before, or it says starting with your fifth term, or like in the example where it was squared, we started with 3 squared, then 4 squared, then 5 squared. Okay? We don't know what our function is yet, but we can figure it out. Explicit formula. A sub n equals a sub 1, which means our first term, the amount of our first term, plus n minus 1 times our common difference. First term, 500, plus n minus 1 times our common difference. To go from 500 to 490, we subtract 10, so we add negative 10. Again, we're going to add negative 10. We add negative 10. And I only say it that way, guys, because our common difference is the number that we add. Okay, it's not an add or subtract. Just like our common ratio, we always multiplied. Same thing here, we always add. So we're going to add a negative 10, which essentially just means subtract 10. But to multiply, we're going to multiply by the negative 10. Means the same thing, it's just a little bit of a notation issue. Go ahead and simplify here. 500 minus 10n plus 10. When I distribute, I have a negative times a negative, which gives me a positive. Combine like terms here, and I get 510 minus 10n is the simplified form of my explicit formula. And that goes in my summation. So 510 minus 10n. Again, you could have put your n term first. Does not matter in the slightest. Our last step here is to figure out what our n value actually is. So we take our last term and solve. So I'm going to subtract 510. Get negative 500. Divide by negative 10. And n is going to be 50, which means 10 is my 50th term. which some of you might have gotten just from 500, subtracting 10 every time to get to 1 or to 10. Cool, if you got there. If not, we substitute in our value of our nth term and solve for n, and we get 50 here. And that is our summation. Summation notation on linear functions here. If the explicit formula for the nth term in summation notation is a linear function of n, then the series is arithmetic. And we can use our formula from the first take note in this section to find the sum. The slope of the linear function is the common difference between terms of the series. And on the last couple, when we put them in summation form, we saw that. So here, since I have a linear expression, I can use my summation formula. So again, in my summation formula, S of n equals n over 2 times the value of my first term plus the value of my nth term, my final term. So we can tell here that our n, okay, remember we take 70 minus 1, ending point minus starting point, and then we add 1 again. Okay, every time that we have n equals 1, it's just going to be our ending value is our n. Okay, if n is something other than 1, that's when we have to check this. So, for the first 70 numbers, we take 70 over 2. We don't know what our first number and our last numbers are yet, but we do know those limits, those boundary points. So we can find a sub 1 by plugging in 1 for n. And we get 8. We can find our last term by plugging in 70 for n. 5 times 70 plus 3, 353. Okay, now we can simplify this. 35 times 341, and we get 12,635. That's the sum of the first 70 numbers here. In B, we do not have a linear function. Okay, we have a quadratic, so we cannot use this formula up here. Okay, this is only for arithmetic sequences. So when we don't have a linear function, we can't use it. We can still find our value though. We're just going to have to find all 7 pieces and add them. So 1 minus 1 squared plus n is 2 minus 1 squared plus 3 minus 1 squared plus 4 minus 1 squared plus 5 minus 1 squared plus 6 minus 1 squared plus 7 minus 1 squared. Simplify here. I get 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. 0 squared is 0, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. I go ahead and add these up. And I get 91. I'm going to have to finish the last part of this example on the next video.